Hello everyone, welcome to today's webinar, Comparisons between 2D and 3D experimental mesoscale measurements to examine slip transfer through grain boundaries in titanium and Ti 525. Before we get started, I'd like to just quickly review how you answer questions in the webinar. You'll see the questions panel on the right side of your screen. You can type in any questions you have there and hit the send button. If you have any issues regarding connectivity and webinar viewing, those will be addressed immediately. All other questions will be answered after the presentation. And if we don't get to any at the end, we will answer you via email, so your questions will be answered. I'd like to introduce today's speaker, Dr. Thomas Buehler. He earned his BA in Applied Mechanics at the University of California at San Diego in 1978, and an MS in Ceramic Engineering at the University of Washington in Seattle in 1980. Thomas worked at Sandia National Laboratory in Livermore, California for 5 years on high-rate deformation. He completed his PhD in material science with a minor in continuum mechanics at the University of California at Davis in 1989 and has been at Michigan State University thereafter. His research focuses on characterization of mesoscale deformation mechanisms and plasticity modeling in titanium-based alloys, tin in the context of lead-free solder joints, and high-purity niobium used in superconducting particle accelerator cavities. With colleagues, he has published over 343 papers with more than 8,300 citations and an H index of 45. He is active in ABET engineering accreditation, and he is an organizer or co-organizer of many recent symposia involving heterogeneous deformation related to grain or phase boundaries. He is also a fellow of TMS. Now over to Tom.
Thank you for the introduction and a chance to present in this forum. There are a lot of challenges to characterize heterogeneous deformation in polycrystals, and really we have a bit of a chicken and egg problem. In the SEM as well as EBSD, we often see slip traces that we use to identify dislocation slip activity. But we don't know the local stress and strain history that caused it. It's hard to measure the local stress state experimentally. We can with elastic strain using diffraction, or we can measure plastic strain in DIC, but that's hard to measure the stress. We can simulate mesoscale slip behavior to obtain a stress strain history, but the outcome is usually not all that convincing, especially in details near grain boundaries. For example, this actual measurement of a tantalum oligocrystal shows a concentration of strain near this boundary, which is not there in the model. And this is a better than average crystal plasticity model. And in fact, this particular grain deforms very differently in these two, the real material versus the simulation. We can also learn a lot about dislocation interactions through dislocation dynamics or atomistic simulations at grain boundaries. But these generally require periodic boundary conditions that clearly are not heterogeneous or complex in terms of the boundary conditions. The mesoscale models allow us to use complicated or heterogeneous local boundary conditions. They just occur naturally in the context of the microstructure model, but we do need physics of the slip transfer process to be installed somehow. And a couple of folks have started to do that. Amit Mishra at University of Michigan, Javier Yorca and colleagues in Spain. But slip transfer through grain boundaries clearly affects the local strain history, which then affects the local stress evolution. So can we actually measure the local stress in a meaningful way to understand how that affects or causes or prevents slip transfer? So that's the motivating question for what I'll share today. I'm going to chase this through comparing and contrasting 2D surface observations with 3D X-ray diffraction-based methods using titanium. Part of what's needed for simulations are the critical resolved shear stresses. That's another story, and we've chased this for quite a number of years, and this is a fairly recent paper where we've pursued that in the context of titanium alloys, and I'm not going to say much about this for the rest of this talk. we're going to focus instead on the parameters that are needed to assess slip transfer, and there's a handful of them. First of all, we need to understand the slip systems that are relevant. In titanium, there's a basal slip, the blue, prism slip, the red, and then pyramidal slip. And on pyramidal slip, we've got two different directions, the A direction and the C+A direction. We also need to pay attention to the slip compatibility factor, where we have, say, a slip system that's operating on a blue plane might be pretty closely aligned with slip system operating on the green plane, but there's some angles, 3 different angles that are used to define how far off of perfectly aligned it is. So this M prime parameter is a convenient one because it doesn't involve this theta, and therefore it's amenable to surface measurements. We also have the residual Burgers vector. That's the difference in the Burgers vector of the incoming and outgoing slip, and that's just simply the difference of the two vectors. And there's a magnitude as well as a direction that's relevant there. There's the sense of direction as well as magnitude suggested in this cartoon. We also need to pay attention to the Schmid factor. That is what defines what slip systems are most likely to be operating. And in the midst of all of this, of course, we have a misorientation or a disorientation angle. Nobody knows how to make mis or dis the right answer, but they're both in use. So there's an angle here that can be found from a little bit of linear algebra type math that's needed to do that. So slip transfer is commonly assessed on the surface using slip traces. And here's a nice example of slip transfer happening across a boundary right here. There's a fairly high M prime parameter of 0.89, a delta Burgers vector of about 0.31 of the A vector. And we see that there is a pyramidal slip plane trace that lines up pretty consistently with a basal slip plane place in this grain through this boundary. So to say whether or not we believe slip transfer happened, there are 6 criteria that we've used to assess that. And if we say that all 6 of these criteria are met, we say that's pretty good evidence of slip transfer occurring. And if 2 or more criteria are not met, then we're going to call that not convincing. So here's an example of a non-convincing case of slip transfer where there's seemingly features that go across the boundary that are correlated, but there's quite a big ledge in this boundary. And that ledge as well, basically says that the deformation processes that occurred in the left grain are different from the right grain because they're not agreeing at the grain boundary. So thus we would expect to see a fairly smooth grain boundary topography along when slip transfer happens, and in a low angle boundary that's almost guaranteed, as in this case. Then we also have some choices to make about what parameters about slip compatibility factor are considered relevant, or what values of residual Burgers vector or Schmid factors for slip systems. So all of these taken together contribute to the decision-making process. And part of that is just having a sorted list of Schmid factors amongst the various slip systems in, say, the right grain here and the left grain there. So between any 2 slip systems, and these are the Schmid factors here, and these are just the slip system labels there. So there's going to be a different M prime parameter for any combination of 2. And in this particular case, which is a nice example case, the highest Schmid factor slip systems happen to have a very high, not quite the highest, but a very high M prime parameter. So that's considered a yes, that slip transfer occurred. So in some prior analysis done in a textured sample of pure aluminum oligocrystal, large grain thin foil sample, an analysis of these sorts of things indicated that M prime divided by delta B is about 95% effective in predicting slip transfer. So that's this region in this M prime divided by delta B on the vertical axis and the misorientation angle. So this blue ellipse represents the majority of observations of slip transfer, and this red ellipse represents the majority of no slip transfer, and there's very little space that intersects. The actual symbols on this plot are for samples of Ti 525, and clearly they're not as well separated. And there's reasons for that. One is that we would expect prism slip and basal slip to be well aligned with each other at angles close to 90 degrees, misorientation angle. And indeed, we see evidence of that here. And there's other complicated geometrical things to take into consideration. We have 4 families of slip systems to consider. So let's see. Well, can we learn anything about this process and from this data set using machine learning? And also, these are surface measurements. Do we see the same kinds of things happening under the surface where it's harder to see? Well, I have one slide here just talking about what we've done on the aluminum case. And if we just use one of the metrics, such as from this list, like the disorientation angle or the delta B, or there's a couple of others here, we can figure out with a artificial neural network analysis how many hidden layers we would need in order to get the best predictive capability. So the number of correct compared to the number of correct plus the number that are wrong. And we get maybe not quite 90%, with just a single metric. And clearly the disorientation angle or the same prime parameter seem to be the best ways to do that. When we allow 2 metrics to be combined, there's many possibilities here, and the best we can get is about 90%. So yeah, it works. And we can use machine learning to sort of get a relationship that can predict to 90% confidence that it's happening. And we only need about 40 examples based upon 100 data sets to have a sufficient ability to train the network. A similar analysis done on the 525 titanium gave similar results, and they're just summarized here, but basically we couldn't get better than an 80% predictive capability, but we needed 3 factors, these 3 factors combined in a way to do that. And interestingly, the Schmid factor turned out to be nearly useless in the case of titanium. And that's probably because the stress states are much more heterogeneous when the slip system are more complex and have different critical result shear stresses. So let's focus for the rest of this time on what's happening subsurface. And we're using 2 X-ray diffraction methods. One at APS beamline, Advanced Photon Source at Argonne Lab, beamline 1, which has a monochromatic high energy diffraction microscopy station. And here we did a tensor experiment with stopping periodically to measure all the diffraction patterns by rotating the sample about the tensor axis and collecting a whole ton of diffraction pattern information. And this is done in over a cubic millimeter of space in a tensor sample in 11 different layers. And it takes a bit of math and effort to sort out what points come from which grains, but it can be done in an automated manner. So the far field detector here provides information from which we can measure the full elastic strain tensor at a grain center of mass. And the near field detector right here provides detailed 3D grain geometry, but that measurement takes 10 times longer and you don't get any strain information out of it. The DAXM method is different. Instead of having a broad beam that illuminates many grains all at once, in this case we have a focused beam that illuminates just along a column where a roughly 1 micron diameter or smaller beam is illuminating material beneath the surface. And I'll say more about the method later when we get to that. Using the HEDM method, we are able to observe twin nucleation occurring subsurface. So here is the diffraction or a pole figure, a C-axis pole figure from one layer. And at 0% strain, there's collection of grain orientations, and then it's pretty much the same after about 1.3% strain, but at 1.5% strain, there's a couple of twins that popped into view, and they remained there for larger amounts of strain. And if we take those same orientations and lay them out spatially in space, then we see that there's a twin and there's a parent grain, and they're very close to each other, which is a good sign that, it's a good measurement. And here, just zooming in on that neighborhood, we see that there's the twin relationship with respect to the parent grain right there. So we did this in 11 different layers and found 13 twins that occurred somewhere during the deformation process. And we do get the grain centers of mass, so we get a population of points in space with their grain centers, and from that we can grow with tessellation an estimate of the microstructure. And with this model, we can simulate the deformation. And one thing we discovered is that the sample that the piece of material that the sample was taken from had actually been part of a bending experiment done many, many years ago, but in the far end of it where there was no obvious strain, but it turns out there was a little bit of a strain gradient, in fact, more than a little, such that it became better to model it by doing some initial compression and then tension in order to get things to match, which I'll show in this next slide. So to think about what does the stress tensor do with possibilities for slip systems throughout the material, if we just look at Schmid factors, uniaxial stress conditions based upon only the crystal orientations present, here's a cumulative probability plot between 0 and 0.5 for Schmid factor. And we see that for pyramidal C plus A and for twins, the majority of them have pretty high Schmid factors. And in contrast, Prism has very, very few. This amount from here to there, there's a very small amount that has high Schmid factors. So these curves reflect the texture in the material. And as we deform the material using the grain orientations that are measured, this really doesn't change much because the crystals don't change their orientation very much. But that's based upon uniaxial stress assumption. If we use the measured deviatoric stress that we have, then we don't have uniaxial stress. And we actually get a different representation of the likelihood for various slip systems to be highly favored. And in this case, we've got the dashed lines here represent the measurements. So this comes from the experiment, the dashed lines, and the crystal plasticity model that we used is the solid lines, and it doesn't agree very well. And it's clear that the experimental data changes a lot more than the model does when we computationally deform it. That's if we just use just tension only. But when we do that initial compression and then deform it, it gets a lot better, but it's still not perfect. So a lot of more complicated things are happening inside that we're only approximating with this modeling. So let's zoom into one particular case where slip transfer took place, or where we think slip transfer took place. So here is the grain that twinned. This is looking down the tensile axis. Here's the twin that formed in that grain. So this is just this is a representation of the grain that came from that tessellated microstructure. And here's a neighboring grain that is oriented. This is the parent grain, and this is the neighboring twin. And so here's the neighboring grain for which C plus A slip system is nicely lined up with a twinning plane and thus generates a twin. And this is looking at the same pair of grains just with a different perspective. But what we have with this information is we can find the resolved shear stress for every one of the variants of twinning that are possible. And as a function of strain, we see that the red dot is the one that was actually observed. So at the point in strain where the twin actually occurred, there's a big change in the resolved shear stress for that twin system when it formed. This is for one particular case. In other cases, it's not so dramatic. So there's a variety of scenarios that we've been able to observe, and this just shows one example. After the sample was deformed, we polished one surface, and here's the EBSD map showing a number of twins that are visible. And we find that some of the grains do not have much of an orientation gradient. Some grains have a large orientation gradient, such as this one. And the ones that don't have much of an orientation gradient are basically red to orange grains, which are the kinds of orientations in which twins can be found. It's challenging to find commonality between the EBSD map and this far-field HEDM data set. So we're essentially comparing a 2D slice with a volume average orientation. So here is a portion of the map from this lower portion of this area. And we see that here's the spatial arrangement of grains for which we found the same orientations in this HEDM data set. But the grains are not in the same spatial relationship. They're kind of confused in terms of the spatial part, which is known to be true as the least sensitive aspect of those measurements. Furthermore, the orientation of the grain in the HEDM is not the same as the orientation in the EBSD. But again, keep in mind, EBSD is just a measurement of one slice through the grain, so that's a whole lot more of the grain is contributing to the opinion of what the orientation is in the HEDM. So they're within 5 to 10 degrees in agreement for the ones that we found. And on this side, it's a bit messier, but the same message is true. Well, the near field grain geometry reveals the twins, because we can see twins here. There's a number of them. And we can actually see the axial grain shape and the true proximity relationship of neighboring grains much more clearly. So we observe twins in this near field in 538 of the 1,500 grains that are present in this near field measurement. So 34% of them have twins. We only observe 13 twins with this far field method. And of those, 6 were totally enclosed within the grain, making the idea of slip transfer less convincing. So let's zoom in and take well, I'll first show a little bit more of the statistics of this. We don't have all that good a match between the far field and the near field data sets. So of 1,700 grains in the far field and 1,500 grains in the near field, there's a good match for only about half. And only about half of the matched pairs are close enough together to be similar to the grain size. And the other half are the grain positions in space in a far field have wandered this way and that. And these are just images of the vectors that connect the near field and the far field measurements. So the far field is at best a crude approximation of the actual geometry, and it's maybe only 50% correct. Well, since we have the near field geometry, we can zoom in and take a closer look at these slip transfer conditions that we observe with a far field, or potential slip transfer, the potential for slip transfer occurring. So here's one where, again, similarly, we've looked at the parent grain and a neighboring grain. And here's the neighboring grain here, here's the parent grain, and this blue thing is the twin that's inside the parent grain. And the geometry of the neighboring grain and the way the slip system is aligned matches nicely with the twin. And it's reasonable to expect that C plus A in this neighbor grain would in fact kick a twin into action in this neighboring grain. So the geometrical arrangement is reasonably convincing. But there's more than that we can do to ask ourselves is how much we believe that this is likely, because we can't prove it unless we actually section and well, even that would be problematic. What we can do is, of course, we can plot the result of shear stresses on all the C plus A slip systems in this neighbor grain, and the purple one is the one that is observed right there, and it's somewhere in the middle of the pack in terms of the result shear that's operating on it. But we can also use the way that the lattice rotates in the neighbor grain. If the neighboring grain has this particular slip system active, then there's going to be a rotation axis associated with that slip system. And that rotation axis will not change very much as that slip system operates, whereas other rotation axes for other C plus A slip systems would rotate more as the sample deforms. So at the point where the twin was observed here, here's strain, and this is the misorientation of this rotation axis associated with each of the 12 C+A slip systems. At the place where this twin popped into existence, that's where the rotation of the twinning of the C+A system responsible for this twin was at its minimum, which is corroborative evidence that really we did observe slip transfer happening in that particular case. Well, let's compare this with some observations that we made about a decade ago in the same material. In fact, really close to the same place even. This is prism slip kicking twins into action in a neighboring grain. And what we found is that if we used uniaxial Schmid factor, because that's all we have to go with, and as well as M prime, we see evidence of slip transfer occurring when M prime is high and when the Schmid factor is high. And we saw mostly prism slip kicking twins into action and only one instance of C+A slip kicking twins into action. So that's really different from what we are observing on the interior. So if we actually look at what's happening in the interior here, we have with the X markers the likely C+A to twin conditions that come from the far field conditions where we have the resolved shear stress on the vertical axis and the slip transfer parameter on the horizontal here. And again, we see the same message. We need a high M prime for this to happen. And the resolved shear stress is sort of scattered. This is sort of a shotgun blast here. So stress is not a predictor for whether a twin is going to happen. And out of the 13 cases, which are the X's that we saw, only 3 of them, these 3 that have the combined circle and X, are actually consistent between the far field and the near field analysis. So the far field is not all that great for doing grain proximity assessments, but if we do the analysis that way, we really don't get much of a difference in what the outcome is. It basically says that stress is not a meaningful predictor for twinning, and we do see some evidence that's reasonably convincing for slip transfer from C+A slip to a twin. So some lessons learned about slip transfer from the high energy HEDM experiments, and also from surface experiments, that this M prime over residual Burgers vector is a pretty good predictor, and it's nice because it's strictly geometrical. We don't need to know the stress state. Slip transfer in a cubic material occurs with really high M prime values, typically well above 0.9. But we see slip transfer occurring at much lower M prime values in titanium, and there's other data in addition to ours that supports that. So the global stress state is not very reliable, but it's better than nothing. Even the grain average stress state differs significantly from the global estimate, and it's clear that there's complicated things going on inside. But this is a more important outcome of this right here, that the free surface does not have the same constraints as the interior for obvious reasons. It's a free surface. So correlated slip transfer evidence suggests that slip initiates at the free surface. And this has been chased in another paper by one of my colleagues. But this all points to the fact that it would really be nice to know the local stress state in places where slip transfer is happening so that we can maybe get a better idea about what's going on. So that's where we're going next. So some years back, we made our best attempt to compare an experiment and a simulation using differential aperture X-ray microscopy. And this involved getting as good of a representation of subsurface grain geometry as we could, comparing that with a first generation as well as a second generation model to see if we could develop slip parameters, critical resolved shear stress parameters, that would enable us to compare a feature on the surface that we could measure with EBSD and also simulated so that we get the similar kinds of features taking place, at least in the grain of interest that we were focused on. And then once we have that, we could compare what we measured with a DAXM with the crystal plasticity simulation, and at first glance, we're getting a number of things reasonably close. We got a green area here and a green area there, and below that a yellow area and a yellow area. But the closer you look, the more discrepancies you find. For example, there's yellow right here at what is a grain boundary, which is missing in the simulation, and there's yellow up here in the real measurement that is not there. So it's still not fully convincing. So we decided that what would be helpful is that if we made our measurements while the sample is loaded with this DAXM method. So here's the geometry of that. We have an incoming white beam, and so we're getting essentially a Lowy diffraction process from many different planes are contributing, and they're collected on the detector. And this gives a cartoon indicating how a moving barrier here basically blocks out diffracted beams as a function of position as far as where the diffracting events are coming from in the illuminated volume of this white arrow. And here's a sense of how much we bent the sample and at one stage. So we focused on a neighborhood that had some heterogeneous properties. This grain that's sort of a yellowish or whitish grain, beige, is a bit harder in terms of its resistance to deformation than surrounding grains, which are oriented favorably for either basal slip or prism slip. And this is just a uniaxial Schmid factor map showing that this hard grain has really different kinds of Schmid factors for different slip systems. So we then did a series of probes with this DAXM method to essentially map out the microstructure of the material before we deformed it. And that's in 3D, so every one of these dots on the surface has a column beneath it that indicates what the grain geometry actually looks like. And so then we had several bend increments from which we made measurements, but at the second bend increment, we made some finer scans in a number of regions of interest, including this beige grain and the neighboring areas, that would allow us to do a deeper dive into the details of what's going on. And that's where, and here you see this finer spatial scans regions that are identifying what the microstructure looks like beneath the surface. From this measurement, we can find the 9 components of the rotation gradient, and just a simple glance at this certainly tells you that this just gives different kinds of rotation axis information. We definitely see a lot more rotation taking place near grain boundaries than in grain interiors. So we can take that information, which are these alpha parameters, and we can take the slip systems that are available to account for lattice rotations, and with that, we can essentially extract the geometrically necessary dislocation density that could account for the rotations that we actually measure. So this is a linear algebra problem that was developed by Das and colleagues, and so this basically allows us a way to find the GND density on every slip system. And so here is, again, the orientation map. Here is the total GND content, and then partitioned out with basal edge dislocations, prism edge dislocations, pyramidal A. There's screw dislocations that can be actually distinguished from edge. But interestingly, here's the C plus A dislocation density in the lower right-hand corner, and there's a lot more density on those slip systems than on the ones that are more active, which is an interesting thing to think about. We're going to look at a few of these areas in a little more detail. This purple grain right here has an interesting band that goes through it that has higher GND content. and very few other grains showed such features, so we decided to take a look there. There's this triple junction with this purple grain and this beige hard grain and this blue soft grain that we'll take a look at as well. Okay, we've got 1 micron voxels for which we know the elastic strains, and if we know the elastic strains, we can find the stress tensor at each of these voxels. And from that stress tensor, we can identify the principal stress directions. If we do essentially what was done in HEDM and just average all of the voxels in the purple grain, this is the average state of stress within the purple grain right there. When we look at the actual stress tensor in location by location, we see some interesting features. First of all, this average value is only found in a few places in this particular slice, in this particular neighborhood, right around here. Most of the rest of the ones that are close to it are tilted a little bit counterclockwise from the way it looks in the average. But even more interestingly, all the ones that are circled in blue here have a completely different local stress tensor. And they're different, but they're also kind of similar, as if this material was sort of partitioning itself into regions with one stress tensor and regions with another stress tensor, which is certainly a possibility if one thinks about developing dislocation substructure in sort of a composite material-like approach. So we see evidence of that, and it means that there's really heterogeneous stuff going on, and certainly at the micron scale, which is no surprise from all the TEM that's been done over the past many decades. But we're actually seeing that here in the form of what are the stress tensors looking like. Okay, let's look at a grain boundary neighborhood with the neighbor to the north or above this purple grain. And we see here's some stress tensors in the bulk of the purple grain. And if you look at the stress tensors in this band that's near the grain boundary, they're all pretty systematically different from what's in the bulk, making sort of a mantle region where the stress is different. And in this boundary, we see some stress tensors right adjacent to the boundary that have much larger magnitudes. So the denser the color, the higher the magnitude of the stress here. Whereas in the rest of this lavender grain, the stress tensors are not as high and they're a bit more uniform. In this triple junction, we've got, here's this hard beige grain, and we see that the stress tensors are pretty uniform. In this purple grain that's below the surface in this particular slice, the stress tensors vary a little bit, and they get a little bit more complicated or different near the grain boundary. And in this blue grain, the stress tensors are much more varied from place to place, and especially near the triple junction here, the stress values, the magnitudes, get quite a bit higher. So what do we do with this information? Well, we can do the same sort of thing that we did on a grain average basis with sort of a 2D analysis. We have a stress tensor here and a stress tensor across the boundary in the neighbor, and we can use those stress tensors to evaluate Schmid factors, and we know the orientation, so we know the M prime conditions, and so we can start doing those kinds of analyses. So we're just doing this with certain pairs of voxels, doing that in this band, which we consider to have, a large density of GNDs, or arguably it might be an undeveloped low angle boundary neighborhood. We can also do that in the grain boundary neighborhood. So we can do the same kind of thing we did in some of the other plots that I showed. Here I'm putting a residual Burgers vector on the bottom axis and M prime on the vertical axis. So again, a low residual Burgers vector and a high M prime. That's what we should be seeing when we have a very small misorientation. and it's from, in this case, basal, blue for basal, basal to basal, and prism to prism, and pyramidal A to pyramidal A. These other symbols that show up are for, say, basal to, prism to pyramidal A or other combinations. There's also a prism to prism, which is not well aligned. And so basically we see what we should be seeing when there's a small misorientation. And so slip transfer would be expected in the upper left corner and no slip transfer in the lower right corner, but they're rather scattered here. In the high angle grain boundary, we see there's some degree of possibility or plausibility of slip transfer taking place on a basal slip system, but less so in a prism slip system, and possibly some mixed kinds of slip cases amongst four voxel pairs that are near each other. But these data points represent four pairs of voxels, and so really to dig into this, one would have to look at each of these cases individually and think about them, which is a lot of work. And we got a hell of a lot of data to do that with. And furthermore, we haven't even considered the impact of the GND density. So how do we use the GND density to help inform us about the likelihood of slip or slip transfer? Well, does GND density indicate activity on a slip system? Does it indicate a lot of slip or a little slip, or is it representing residual debris or some mixture of all three of these things? Well, we can begin to think a little bit about what this might be helping us see, because if no slip transfer happened due to the grain boundary being one that blocked slip, then we would expect a high GND density. And conversely, if slip transfer did happen, then there should be relatively few GNDs because the dislocations pass through the grain boundary. And then we also have the question about which side of the grain boundary was the initiating side for slip transfer, the one with a higher Schmid factor or the one with a lower GND density. And so there's lots of additional things to think about. So here are some possibilities for how we might incorporate the GND density into metrics such as the residual Burgers vector and M prime parameter. And so I won't go into these details, but here are some approaches to start asking that question. So let's ask that question with respect to this triple junction here. So here's four pairs of voxels that we're going to be doing that calculation and just seeing what falls out. So in this case, we're taking M prime and dividing it by one of these dislocation densities on one side or the other side of the grain boundary. And here, because the dislocation densities vary by orders of magnitude, we're putting this on a log scale. And like anything that you put on a log scale, everything sort of comes out as a line. So again, in the upper left, we would have a situation where we would expect to see more likely to be slip transfer and conditions that are less likely for slip transfer to the lower right. And then we also have to ask ourselves, well, let's assume the basal slip was an initiator. What would we see with respect to that? And this is using the maximum of the dislocation densities versus the minimum of the dislocation densities. So we get a variety of different outcomes here. I'm not going to attempt to try to explain them, but we have data to chew on. And if we compare these three different grain boundaries, like the grain boundary that's on the surface between the soft and the hard grain, and the grain boundary that's below the surface between a soft and a hard grain, and a grain boundary between two soft grains that is below the surface. In a sense, every boundary is different in terms of a kind of personality, if you will, of what kinds of slip interactions are there or could be there. And so there's a lot to think about. And this is the same thing using the minimum GND density. This is the maximum GND density of what's on either side of the boundary. So we're just beginning to figure out how to think about this. So since I don't have any real strong answers yet, but just simply the main message is that this is complicated. And it's clearly the degree of heterogeneity increases as we get to decreasing size scale at which we can make measurements. It leads, of course, to much more detailed data to consider, and with that comes the complexity. It's clear that local stress states vary wildly, even from one voxel to the next, and in various ways in different boundary regions. Even in some intragranular areas, the stress state is uniform, and in other regions, highly variable. So this vast amount of data certainly makes it possible to do lots of systematic study and analysis, challenging our imagination to find meaning. So are we seeing what we want to see? Or is it chaotic or some combination of those? It's clear that we're basically overwhelmed with data, and we could chew on this for a long time. So an ongoing question is, what is the meaning and value that we can extract from knowing the GND measurements? So I have more questions and answers at the end of all this, but it's certainly been an interesting journey, and I thank you for joining me for a quick look at this. So with that, I'm happy to field some questions.
Hi, everyone. This is Stuart Wright. I want to thank Tom Beeler for his presentation and walking us through this difficult world of slip transmission. I know I've got some questions for him, but I'll be the moderator for the questions today. So if you have any questions, please continue to add them. Tom, I had one question for you. Does the M-prime relationship hold for lower symmetries materials, like say in rocks and things, or does that break down as the slip systems get more limited?
Well,
do you have a feel for that?
Yeah, I have a very quick and easy answer, and this has to do with the M-prime parameter is only meaningful if slip is happening. Otherwise, it's moot. So if there's no slip happening, then there's no point in even asking the question about what M-prime is. Now in rocks, that still can be interesting under cases of long times or higher temperatures, because dislocations do happen in rocks in geologic timescales. So yes, it could be relevant.
A question from the audience. What is the effect of lattice rotation or lattice curvature on slip transfer? That's a good question. I think, we've been seeing, you've been showing planes, but as things get curved, how does that affect things?
Well, certainly this brings up a whole nother point. When we are, if we want to really ask the question of what's going on at a grain boundary, we need the local grain orientations. And clearly, if there's a gradient in the grain orientation as you approach the boundary, then the average grain orientation is not necessarily going to be, as relevant as the local grain orientation, which is why EBSD measurements, or in this case, DAXM measurements, are probably more useful for chasing this question. And then adding to that, another complexity is that the evolution of the lattice curvature occurs with increasing strain. So what may be true at an early stage of strain in terms of conditions favoring slip transfer could change as the lattice rotation changes. So there's a whole dynamic component to this that we've hardly even asked that question. And that's an opportunity for digging in deeper and getting the time resolved aspects of the. And one possible scenario of this, suppose slip transfer is happening a lot at first, but then as the lattices rotate, it shuts down, or vice versa. So that introduces an evolving slip transparency that can be quite local in any particular grain boundary. And it evolves.
So I guess as we enter the world of deformation and deformed materials, that the idea of a grain having a single orientation probably is not the right way to approach them. And that's probably why the models, a lot of the current models, start to fall apart.
Well, ideally, the current models are capturing the lattice rotations, because essentially the grain boundaries provide a kind of evolving boundary condition on any local grain neighborhood.
Right.
And so we have evolving boundary conditions everywhere. And the question is, how big of a volume do you need to define what the local boundary conditions are to make a meaningful assessment of what slip systems are most favored? It's sort of like the question of what is the GND density? It depends on the size of the volume that you want to measure over. The smaller the volume, the fewer GNDs there will be. So,
Yeah.
I mean, this stuff all gets kind of fuzzy the more you zoom in. And I think, you know, the data I just showed is sort of indicative of that.
One other question is, do you expect slip transmission to be active between say a compression and a tensile twin? I would assume the stress states in those two cases would be different enough that it would be unlikely, but is that my thinking incorrect?
Could you ask that one more time? I'm not sure I caught the sense of this.
So if you've got a compression and a tensile twin that happen to be in the same neighborhood, do you expect those two to interact in some way? Or will the states surrounding those twins be so different that it would prevent that?
Well, often, at least in magnesium, you see compression twins within tensile twins. And so, yes, they are spatially in the same neighborhood. And I do think that I haven't spent a lot of time looking at, I haven't looked at magnesium, but from people who have, damage tends to be rather severe in neighborhoods where twins intersect. And, you know, that's an even more complicated space to think about. And I just have avoided that because I have plenty to do with what I have.
That makes perfect sense. Well, that wraps up all the questions that have been posted today. If you have later questions, feel free to contact us or contact Tom on this interesting area of research that I think is probably growing more than shrinking due to the complexity of what we're working with here. So once again, I want to thank Tom and all the efforts he's put into both the research and also making this presentation on our webinar. And thanks to everyone for joining us.
Well, thank you for listening as well.